Good morning, everyone. My name is Xinyu Gao. It's my honor to stand before you today to talk about a cutting-edge advancement in the field of software engineering and artificial intelligence, our novel framework for retrieval augmented code generation, which we aptly named RRG, short for Retrieve, Refactor, and Generate. A fascinating domain lies at the crossroads of software engineering and artificial intelligence, retrieval augmented code generation. This field has been gaining significant attention due to its potential to revolutionize how we write code. The core idea behind RACG is to leverage the power of LLMs as generators and enhance their capabilities by providing them with relevant code, documentation, and other resources through a retriever. In a sense, RACG is about augmenting the intelligence of code generators with external knowledge. Imagine you are working on a complex software project that requires a specific function, say a sorting algorithm optimized for a particular data structure. With RACG, instead of starting from scratch, you can describe what you need, and the system retrieves relevant code snippets from vast databases. These snippets serve as a foundation, which the generator then uses to produce a tailored piece of code that fits seamlessly into your project. However, this process is not without its challenges. The indiscriminate inclusion of redundant information can lead to resource wastage and may misguide the generator, affecting its effectiveness and efficiency. Moreover, there is often a preference gap between the retriever, which seeks to provide code with high ground truth similarity, and the generator, which may prefer code that is more aligned with its internal knowledge and optimization objectives. In the realm of RACG, the retriever's role is to search through vast code repositories or databases to find snippets that are relevant to the task at hand. While this sounds efficient in theory, in practice, it often leads to an overwhelming amount of information being retrieved. This indiscriminate inclusion of redundant information is the first limitation we identified in RACG. When the retriever pulls too much information, it can result in several issues. Firstly, there is a problem of resource wastage. The process of sifting through excessive data is not just time-consuming but also computationally expensive. It requires significant processing power and memory to handle the overflow of information, which can be particularly challenging for systems with limited resources. Secondly, and more critically, the inclusion of redundant information can actively misguide the generator. The generator relies on the context provided by the retriever to produce accurate and efficient code. However, when this context is cluttered with irrelevant or repetitive data, the generator's performance suffers. It becomes difficult for the generator to identify the core elements necessary for the task, leading to code that may be bloated, inefficient, or even incorrect. In RACG, the retriever and the generator are two distinct components with different optimization objectives. The retriever is designed to fetch code snippets that closely resemble the ground truth, aiming to provide the most accurate and relevant information to assist the generator. However, our research has revealed that there is often a mismatch between what the retriever considers useful and what the generator actually prefers. This discrepancy is what we refer to as the preference gap. The generator, which is typically an LLM, has been pre-trained on a diverse range of code and may have developed a preference for certain coding styles, structures, or patterns that are not always aligned with the retriever selections. For instance, the generator might favor code snippets that are more concise, have a clear structure, and introduce novel knowledge not already incorporated into its pre-trained parameters. On the other hand, the retriever might retrieve code that is more verbose or complex simply because it matches the ground truth more closely. This preference gap can lead to suboptimal code generation. Even if the retriever successfully retrieves high-quality code snippets, the generator might not effectively utilize this information if it doesn't align with its preferences. As a result, the generator's output may not be accurate or efficient as it could be, limiting the overall effectiveness of the RACG system. So we propose our method RRG. The framework operates in three main stages. First, retrieval. This is where our retriever does its job, searching through vast databases to find relevant code snippets that could assist in generating the desired code. Second, refactor. This is the heart of our framework. Here, a code refactor module takes the raw retrieved code and transforms it. It eliminates redundancy, reduces noise, and refines the code into a more concise and efficient format that is friendly to the model we will use for generation. Third, generate. With the refactored code in hand, our generator can now produce the final code. Thanks to the pre-processing in the refactored stage, the generator receives higher quality context, enabling it to generate more accurate and efficient code with lower inference costs. RRG is trained through a two-stage process. First, we use supervised fine-tuning (SFT) to train the refactor for generative compression, during which we also integrate external knowledge. Then, we fine-tune the refactor to align its output with the generator's preferences using a technique inspired by reinforcement learning. In a sense, RRG is about refining the raw material of code retrieval into something more polished and generator-friendly, ensuring that the final output is not just code, but code that is clear, efficient, and ready to use. It's an approach that turns the promise of AI-assisted coding into a practical reality. In stage 1, we focus on training our code refactor to simplify and compress the code retrieved by the retriever. This stage is crucial for teaching the refactor to strip away unnecessary details and retain only the essential parts of the code that are relevant to the task. By doing so, we ensure that the generator receives a clean and efficient code snippet that's easy to work with, which ultimately leads to higher quality code generation. This fine-tuning process helps bridge the gap between the raw retrieved code and the generator's needs, making the overall system more effective and efficient. In stage 2, we refine our code refactor to align with the preferences of the generator using a technique called preference-aware tuning. This stage is pivotal as it ensures that the refactor produces code snippets that the generator finds most effective for generating accurate and efficient code. By leveraging reinforcement learning, we adjust the refactor's output to better match the generator's preferences, resulting in a more cohesive and optimized code generation process. This tuning phase is essential for enhancing the overall performance of our framework, ensuring that the generator receives context that is not only relevant but also tailored to its specific needs. We conducted extensive evaluations on two datasets. These are CodeSearchNet and Concode. Our experimental setups are as follows. First, the retrievers are PM25, UAE Large V1, and Embed Large V1, and the generators are GPT-2, CodeGPT, CodeGen, and Polycoder. And finally, the matrix are Exact Match EM and Blue and CodeBlue. Our research questions are as follows. RQ1, does the RRG framework improve the effectiveness over RAG? RQ2, what is the effect of various retrievers on the performance of the RRG framework? RQ3, how do code tokens of varying lengths influence the RRG's performance? RQ4, what is the impact of the preference-aware tuning stage on RRG? RQ5, how is the generalization performance of the frozen refactor? Does RRG framework improve the effectiveness over RAG? In most configurations, RRG can significantly enhance the performance of the generator and reduce its inference costs, demonstrating the robustness and effectiveness of RRG. What is the effect of various retrievers on the performance of the RRG framework? The RRG framework can perform well when using different base models as retrievers. Moreover, in code generation tasks, there is indeed a preference gap between retrievers and generators, and RRG can bridge this gap. How do code tokens of varying lengths influence the RRG's performance? The setting of different code tokens has a significant impact on the code generation performance of RRG, with this difference reaching 12.02% and 30% on two datasets respectively. What is the impact of the preference-aware tuning stage on RRG? The preference-aware tuning stage is crucial, as it further enhances the effectiveness of the RRG framework by considering the preference of the generator. Moreover, it exhibits good generalization, potentially yielding better results on complex datasets. How is the generalization performance of the frozen refactor? The frozen refactor demonstrates strong generalizability, suggesting its advantage as a modular plug-and-play component. In practice, it can be directly transferred between different retrievers and generators without requiring fine-tuning. And that's all. Thanks for listening.